Hello and welcome to lecture 16 if I'm counting correctly. So this is the slide that we stopped on last time, but before we get to that, let's go over a couple important things that will matter to you in a little bit. So I've added this page on our course website under information, then grades. So after the final is graded, on this page, you can come here, enter your perm number, and I'm going to give you a complete breakdown of all of your grades, okay? So everything compiled together, and then like your final letter grade as well, and then you can yell at me if anything looks weird or wrong, okay? So that's the idea there. Please go there after the final is graded, and I'll of course remind you once that's done. Okay, so that's grades. Now, also, let's go and take a look at any questions that we have for today's lecture. And it looks like there's just one, and it's about how do you count in hex. So, for example, it looked like I added 4 to 8028 and it went to 802C, and maybe that was a bit confusing to understand how to do. So I will talk about actually addition in binary and hexadecimal today in depth. So just wait a little bit later and I will get to this answer. So that was really good timing. But you also have enough information to do this on your own, even without this extra stuff that I'm going to tell you. There is a way to do it. So if I want to add 4 to 0x8028, the first thing that you can do, because this is in hex, you can convert it to decimal and then add your 4 and convert that back to base 16. So you can always get this value, but I'm going to show you like how the math works if you're just going to add things in hex only today. Okay? But there are ways to get around that if you don't like this idea that I will show later. So I will be getting into this, so I will be, let's delete this one. All right, so I think we are good for now. Maybe I can go back to this page. So let's start off where we left last time. So you might have to go back and look at the end of last lecture to remember how we came up with this base case and this recursive case for this implementation. But now I'm going to go and actually code this up so that you have this to look at and study from. All right, so we're remembering that we're trying to delete some value inside of a list recursively. And we came up with the base case and the recursive case for how we might do this. So I'm going to copy this code from, looks like lecture 14 with a bunch of list stuff, just so that I can have a list to work with and all that boilerplate done for me. So I'm going to copy and paste all of this into today's folder, and we'll call this delete recursively, I guess. And yes, did I spell that right? All right, so we're there. Now, so we don't care about min anymore. We don't care about min. And I think the rest is just adding stuff to lists and list definitions. So now we are set. So here we have made this list 10, 50, 20, 40, and let's pretend that we hate the node with 50 in it. So let's call our delete recursive function on our list L. How do I want to do this? Yeah, let's do a helper function as well. So we're gonna make two functions, one that takes the list and then the other recursive function that actually does the recursive thing on the node star. All right, so let's give it the L, and we want to delete all the nodes with 50 in it. And then maybe we can have a print list function to make sure that we got rid of it. And then let's also, because we're gonna end up with 10, 20, 40 after that, let's also make sure that we work with the head, because that might be like a special case. So let's make sure that the head can go away as well. So let's remove the 10, then print L again. All right, so that's the idea there. So now we have to make these two functions. Print list is easier, so let's do that one, just to get some experience with printing things. We can do this iteratively or recursively. Gosh, I think you've gotten enough practice with iterative things. Let's just go all recursive today. So I'm going to print a linked list recursively, and I'm going to go through this a bit faster. Let's see here. It's just like printing an array recursively, very similar. So given a linked list, I want to print you recursively. Well, a linked list type itself is not a recursive type, so I want to call a printlist helper function on the head of that list. That's the same reason we're making two functions here, because node star is what we can recurse on, because head next is another node star, but list head and list head next is not a linked list anymore. It's now a node. So we want to stick with nodes, and that is what allows us to have a recursive function. So let's now make our print list helper function that takes no longer a linked list, but a node star. Again, it's void because we're just printing stuff out in this function. And this is a node star. Let's just say n, or technically it's the head of the current list we want it to consider. So let's just do it like that. And then of course, so this is a recursive function. Either the list is empty or it's not. So if the list is empty, we know that head must be the null pointer. If so, we can output the fact that it's the n, so maybe we can say x or something. Otherwise, let us print out, yeah, let's have an else statement. I don't want to just return for no reason. Otherwise, we have a non-empty list. So let's print out the head. That's the first thing that needs to happen. And then we can recursively print out the rest of that list. So head data, we're going to print that out. And then we can also print that arrow. And no new line just yet. We can have the x print out the new line at the very end. And I encourage you to draw the stack for this as it's printing out on an example list. So then we just need to print the rest of the list recursively. Print list helper, it's a recursive function. It takes a list, prints out a list. Let me give it a smaller list, and I get to assume that it's going to print it out properly. Head next, so this is going to print the smaller list, and I do that after I printed the heads data, and that's going to correctly print out every value in the list. Yeah, looks good to me. We'll see if I made any silly mistakes. So that's print list, and now let's go to the main thing. So we're going to do the same thing. We're going to have our delete node recursive, or we called it delete recursive, so let's just change that. There we go. And that's going to call our recursive helper function that actually does the work. Okay. Call helper. So delete node recursive helper with list head. That's where the list starts really, and we want to delete that same value that we were given in this function. All right, so now we can actually implement all this stuff over here, which it's a lot of words, but it's actually quite quick in terms of implementation. This was just getting all the ideas on the page. So in the base case, we needed to delete all of the nodes with a value of the given value, but there are no nodes of that value possible in an empty list, so we can just do nothing. So if head is the null pointer, base case, empty list, as usual for linked lists, do nothing. You can't delete anything from an empty list, and the result is still an empty list. So result is an empty list still. And remember that we're giving back the result of deleting everything in this list with that value. So we're always giving back a list. So remember to give back the updated list with value deleted from all the nodes. So in order to do that for us, in this case, we just return back the null pointer, return back the empty list that we got. Otherwise, now we're in the recursive case. Non-empty list. So the first thing that we can do is make the recursive call on the smaller list. So we know it's going to delete the thing properly as long as we build up the final list correctly. So let's say node star smaller list with value deleted from it. And this is the head of that smaller list. Head of smaller list with value deleted. That's a very long variable. It's, if you ever get into Java, you'll see plenty of these. So that is the result of calling our function, because it gives back that smaller list, changed. Delete node recursive helper with the smaller list, so pointer to the start of that. Delete that same value, please, and let's get back a list with all those values deleted. We get back. Can assume that we get back a pointer to the head of a new, smaller list with all nodes where data equals value deleted. Okay, that's the idea. That's what recursion is giving us. And now it's our turn to do real work. So we have to build up the proper answer correctly now using this assumed correct answer for the smaller list. That's the reason recursion works. So we have to now consider our head, that one node that we haven't looked at yet. And so we either need to keep it or not, depending on whether the head's data is equal to value. All right, so if head's data is equal to value, we better delete our own head. All right, so let's do that. Delete head. That node needs to go away. We don't want it anymore. And delete isn't really a function, but you can call it like one. So delete head, and now the result for the entire list is the modified smaller list, because we're not keeping the head anymore. All right, so the entire result for the bigger list is the result of the smaller list because we're getting rid of that head. Otherwise, head's data is not equal to the value, and we keep it. We keep it around. Head stays. All right, and in that case, we are eventually going to return head because that's the same list. Return the modified list with head still in it. But it's quite possible, and it's exactly going to happen, that we might have deleted heads next. So if this was our list and we wanted to delete 20, and we were in the first recursive call where this is our head right now, that makes this our head next. When we made that recursive call, we're going to get back the list just containing 30. And you see how we need to put 10 in front of that 30. So that means head's next. Its pointer needs to change. Okay? It needs to become that modified smaller list, because it's quite possible that heads next is not what it used to be. It might have been the value that we needed to delete. Because we might have deleted its old next node. Okay, that's the idea. And so in that case, we return that list back to ourselves, and that is the result of the whole darn thing. So maybe let's just first confirm that all this is working, and then I'll draw the stack diagram for maybe the first recursive call, or the first call to that function. All right, and you can walk through the code. So let's go into lecture 16. Make that program for me, please. Let's see if we made any mistakes. All right. Delete the 50, delete the 10. Oh, I definitely made a mistake here. The first time that we called this function, it worked just fine because the head wasn't changed. But oh man, I wanted to change the head this time. And I did everything right in the delete node recursive helper function, but this list still had a head and a tail pointer that I never looked at. So, shame on me. Node star new head is the result of this value. And it's quite possible that some weird things happened. So it's possible that the tail changed as well. So we better find the new tail. And I'll just use iteration for that. So I hope you see what happened here. I didn't just have this list 10, 20, 30. I had my L pointer to a linked list object that held 10, 20, 30. If I just make up the values, I know those aren't what they really are in this program. But here's what I was doing. I was totally deleting this list properly, like I got rid of this head. And so this was the list that was given back to me if I deleted the 10. But what I forgot to do was change this head pointer, just like that. And it's also possible that we deleted the 30, in which case the tail pointer needs to be there. Okay? So we need to also keep track of this stuff for the linked list itself, this variable. All right, so let's go and fix that. So we know the new head. And so now let's go and find the new tail. So node star new tail. We just need to find the end of this list. Equals list arrow head. And let's just keep on going. So while new tail arrow next is unequal to the null pointer, it's quite possible that we deleted everything in the list. So let's have two cases. So if new head is equal to null pointer, that means the new tail must also be null. Okay. Dun, dun, dun. No, new tail equals the null pointer as well. And then otherwise, we at least have one thing in our list, and so we can actually iterate in the way that I want to. So starting at the head, keep going until we find the last node. That is the node whose next pointer is null. All right, and we know we at least have one node in this else case. I had to check myself because otherwise I would have gotten a seg fault. All right, so we know at least one node is in this list, so we can iterate like this. So we're just going to keep on going. New tail equals new tail arrow next. Keep on going until this is false. Now we know we're at the end of the list. Now new tail is in the right spot, at least in theory. So then list arrow head becomes new head, and list arrow tail becomes new tail. And I think finally, if we run all of this, it should work. It's very important to make tests, though. There's probably something that I made a huge mistake on, and if you see that, please yell at me, and I will apologize. So now it looks like it's working just fine. So let me walk you through what's happening on the stack for this function, just in terms of this first call. So we are in main. Remember where we are. And I need a lot of room, so let me go like that. We start off in main. All right, and then I'll just do a lot of shorthand here. Then we called our delete node. We called our delete function with value being 50 the first time. And we called it on the list. I'm just being very not correct in my diagram. That's okay. 10, 50, 20, 40. So take a look at the code as I do this. The first thing that we do is call our helper. That actually does the recursion. On the list, 10, 50, 20, 40. And we still want to delete that 50 value. All right. And what it does is it first goes and tries to delete all that stuff from the smaller list. So it's going to call the helper with 50 on 50, 20, 40, which is going to itself call the helper because it wants to initially delete from that smaller list so that it can build up the final answer. 20, 40. Always delete that 50. And again, helper on just the list 40. Still delete the 50, please. And finally, the helper on the 50 with the empty list, which is the base case. And so in this case, it's going to do no work, return the empty list. That's the result of deleting all the stuff in the empty list with value equal to 50. And this is going to then consider, take that empty list as fact, or take that smaller list as fact that it got back. That is the result. That is the correct result. And now it needs to worry about its 40. Well, it's not 50, so we'll keep it. This will return back the list with just 40 in it. And similarly, this will return back the final list, 2040, because it got back the list 40. And it'll add its 20 because it's not 50. So it's given back 2040. And finally, we're actually deleting something, so we're not including the head. We're calling the delete function here. So let me underline this 50 in red, maybe. And we're going to return back, well, the correct list is just 2040. So that's what this helper sees. And now it considers it's 10. Make sure to set the next pointer to be the correct new list that we got back. We don't want anything to go wrong there. So it puts the 10 in because it's not 50. And so we finally get back 10, 50, or 10, 40, 2040, sorry. And that's what the delete list sees, and then it fixes its head and tail stuff. And we're done, and we can print everything back in main. All right? And so remember, when all these return, all these stack frames are going away, but that gets ugly. So I hope that makes sense. And that is the last big example, a whole 119 lines of that. Okay, so that is that slide. The rest of these slides, it would be a little evil for the last week of class. We're going to test you on all the new knowledge that I'm about to give you. So I'm not going to test you on this stuff, but if you take CS24, you need to understand this. So that's why I'm giving it to you. Please watch this and understand these things, especially if you're going to take that class. And this is fun stuff, I think. They're fun little examples. So let me check my time. Doing all right. So the first thing that I want to talk about is how to search for a value in a sorted array. And this is a algorithm called binary search. And it's very fun and it's very fast. It's quite efficient. And efficiency isn't something we really care about in this class, but in future CS classes, it'll be very important. So binary search is very efficient. It's fast. So if I was trying to search for example, 50 in this array, and I wanted to return back the index where that lived, like I wanted to find the 4, the standard way to do it, or with the knowledge that you have right now, a common way to think about implementing that idea of finding where in the world is this 50 in the array is to start iterating. So we start our I at 0, so I equals 0, it's not there, I equals 1 now, it's not there, I equals 2 now, no, it's not there, I equals 3 now, still not there in the array. Okay, I equals 4 now. We found it. We can return back 4. That's the answer. That's the index where the 50 lived. Okay, imagine that this array wasn't size 8, but was size 1,000,000. And this was somewhere in the middle. It starts to take time to search through it, okay? It might be quick and fast if it's a small array, but once it gets big, things go bad quickly. So the idea for binary search is we can cut off our search space, we say. It cuts off its search space. We say like that. And the idea is we keep on making a guess as to where it can be. And we use the fact that this is a sorted array. That's very, very important, okay? Binary search does not work if the array is not sorted, because then we don't know. We don't have any guarantee as to where this thing might be. All right. So, and the strategy is something that I think you already understand. So if I asked you, I'm thinking of a number between 1 and 100, just randomly, what is the first number that you would guess to make it so that you can always guess efficiently, to ask the minimum number of questions and get the number right? I think you would say, okay, I'd start guessing at 50. And if I told you, okay, your number is too low, you would then guess 75, right? And the idea with that is, well, all right, if I had numbers from 0 to 100, or 1 to 100, first you're going to guess 50, and then use that information I'm going to tell you, okay, it was too low, so let's start guessing higher. Now you know the number has to be here, and you never have to look here anymore, okay? Let me just write all that out. So like, I'm thinking of a number between 0 and 100. You'll guess, is it 50? That's the optimal guess. Optimal first guess. Assuming I pick randomly. And then I'll say, no, guess that was too low. And now you'll guess higher, because now you know can't be here. Now you have fewer things to search inside. Okay, that's the idea. And that's the same idea for binary search. So if I want to find this 50 node, I first cut this array in half, go to the middle index. So for binary search, first cut the array in half and go to the middle and see what the value is. If it's smaller than what you're looking for, so say I was looking for that 50, but it was 40, then you know to guess in the upper half. Otherwise, you'll guess in the smaller half. If you didn't get it, that is. Eventually, you'll land on the index if the number you're looking for is actually in the array. And the reason this is so fast is, all right, let's say you guess 75 now. And then I say, all right, that was too big. Now you know it's right here. You keep on cutting your search space in half. You keep cutting your search space in half. And so you get to, how do I want to say this? And so your search space gets small exponentially fast, we say. All right, so that's the idea. And so keep in mind that you can only divide by 2 so many times. You can only divide 100 by 2 log base 2 of 100 times. That's really not a lot. Even for very large numbers. And that's log base 2. I want this to go on the next line, please. There we go. Okay, so that's the idea, and now let's code this up. So it's always about making a guess and seeing if our guess was okay. And I think this is a good time to talk about this cool new array replacement data structure called vector. It's in its own little library header called vector like that, and it's exactly like an array, but it can change in size. It doesn't have to be initially defined to be a certain size, which is beautiful. So I'm going to use arrays because they work just like arrays in a sense. I'm going to make this exact value here, right? Let's see here. Binary search.cpp. So I'm going to include IOStream. I'm also going to include vector using namespace standard. So I'm going to make my main function. So instead of int arr equals 1, 2, 3, I can say vector bracket, angle bracket, int, closing little bracket, v equals 1, 2, 3. And the beautiful thing about vectors is I can add to this, whereas I'm stuck with a vector of size 3 here, which is no fun. But a vector, I can add more. I can use this operator called dun 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 push back, add an element to a vector. It's just like an array still. I can say v dot push underscore back 4, 5, 6, 7. And did I want to start at 0? No, I want to start at 10. 10 to 80. All right. 20, 30, 40, 60, 70, 80. Now, the vector is size 8, which is beautiful. So you can think of arrays as like someone with like a type A personality. They're like, all right, my size is 3. Only 3. No more, no less. That's as many things as you can put in me. 3 is my favorite number. Whereas a vector is quite a bit more laid back. This person's like, all right, I hold 3 things now, but just wait, I can hold more. No big deal. Let's see how many things I can hold. I have a million hands, you know? It's a very nice person. Okay, so we have our array, or vector in this case, and so now let's do binary search. So let's see out binary search, and let's say we want to search for 50. We want to search inside of the vector for 50. And this will give back the index if it exists. And it's quite possible that it didn't exist. So we want to return back the index if the value existed in the vector slash array. Otherwise, return -1, because that's an index that does not exist. Never exists. Vector int, and you could pass it along by value, but it's a bit more efficient to pass it along by reference. And because we're not going to change anything, we can call it a const vector. All right, and so then also we're going to pass along int value to search for. Did I say any name for it? Just like, I don't know, value. All right. So the idea is start in the middle. So int mid equals, I don't know. Also, a very nice thing about vectors is it knows its length. That's something I didn't say. So you can either use I can just use the size function that tells you how big the vector is. So I didn't have to pass that along. Mid equals v dot size divided by 2. All right, so that's like the midpoint of this vector slash array. You could replace all of this with an array and it would still work. No worries. All right, so now I have the middle, and so keep having the search space while there still is a search space. And so kind of a better way to think about this is to start with your indices. Like, keep track of the low point of where you're searching, like, so the beginning, which is like index 0 in this array. Like, so this, I'm going to start searching here. This is the lowest value that I can search in, and this is the highest value that I can search in. And as you make your guesses, they'll change so that your search space gets smaller. And I'll call this like low and high. And eventually, low becomes here in this case, because we need to guess a bit higher. All right, so low equals that, int high equals v.size -1. That's the last index in this array. And so instead of this, now I can just say low plus high divided by 2. Okay. So let's see how we want to do this. Well, there's still a search space. So let's put this inside of a loop. While low is less than or equal to high. I'll show you why that's useful. So calculate the midpoint and see if we found what we were looking for. So if the vector at that midpoint just so happened to be the value that we were looking for, well, let's return mid in that case. We found it. We're done. Otherwise, if it's less than the value, this means that the search space needs to change. We guessed, let's see, which side are we on? So if what we're looking for is bigger than where we searched, we need to change. We guessed too low, okay? So our low needs to become mid. And I'll show you why that works in a second. And high can stay where it was. Else, in this case, we know that if you just do process of elimination, you know that this has to be true. V mid is greater than value, so we guessed too low. Or we guessed too high, sorry. And so the value that we were looking for was smaller than the midpoint. So we need to change our high to be mid. Right? And actually, because we knew that mid was not the value in both of these cases, we can say low isn't just mid, it has to be from mid plus 1 onwards, and high has to be, in this case, from mid minus 1 downwards. Okay? And I'm going to give you an example in just a second. I'm just going to get this all finished. And that should essentially do it. And yeah, so if we get here, we were out of luck, and we'll return -1 because we couldn't find it. What we were looking for. So let's just make sure that this is working. So I'm looking for 50 in 10, 20, 30, 40, 50. So it's 0, 1, 2, 3, 4, 5 at index 5. Wait, what? 0, 1, 2, 3, 4 at index 4. That's what I thought. All right. Let's see if this prints out 4 to us. And if that's true, I will walk you through why it's working. Dun, dun, dun. If you want to use that fancy thing, you have to compile with C++ 11, G++. Oh, sorry, I need to say output as binary search. I don't want a.out. All right, so we get 4. So let's see why this is working. And can I just copy this maybe? So the idea is, and then I'll show you an example of it not working, or it not finding what we were looking for. So we want the 50. So we're going to start with low equals 0 and high equals 7. And so we're going to do 7 minus 0 divided by 2, which using integer division will give us 3. So this is our mid initially. All right. And so the 40 that we found was too small compared to our value, so we're going to swap low. We're going to change low. It's not going to be what it was anymore. It's going to be mid plus 1. All right? This is our new low. I don't know how I want to do this. Let's say I'll use another color. All right? And so that is the old mid. Now mid becomes 4 plus 7 divided by 2, so that's 10, 11 divided by 2, which is going to be 5, I think, integer division. So this will be our new mid. And it was a little too big, so that means we're going to change our high to be not what it was. It's going to be mid minus 1. So we're going to make our high the same 4 index as well. And so now, in our last iteration, low equals high, so low plus high divided by 2 is going to be the same place. So here is our new mid. And oh man, was that equal to the 50? And we can return our index 4. All right, so that's why it's working. If it's there, it'll keep on doing cool stuff and having that search space and eventually getting there. In the case where it cannot find the thing. Oops, come back, I don't want you there. In the case where it can't find the thing, what's going to happen is, let's say we're looking for 10. Or let's say we're looking for 9. Like we're searching for 9, it's supposed to be way over there. All right, example, search for 9. So here's our low, here's our high. eventually, so here's our mid. Our first mid is here. Or no, it's 3, sorry. Our first mid is 3. And then high needs to change to this, because we guessed 2 high initially. There's our high number 2. And this will be our new mid. And it was still too big, so high becomes low. High number 3. And so now the new mid is also index 0. This is mid 1, this is mid 2, this is mid 3. And it was still too big because we're looking for 9 and somewhere over here, right? Well, that means now high, given our implementation, high gets smaller than low. And that makes no sense at all. It's trying to be like, search from index 0 to index -1, please. And whenever high passes low, whenever those two indices swap, or vice versa, the value was not in the array. That's the idea, and that's why it works. So that is binary search in a nutshell. Let's see how we're doing on time now. Okie dokie. Now you can use the same concept to find the square root of a number, and it's still just a bunch of guesses, because, let's say it's for positive numbers, of course. So here's the graph of square root. It is monotonically increasing. That's the beauty. So we can always make a guess as to what we think the square root of, say, for example, 2 should be. And if it's too big, we'll guess a bit smaller. If it's too small, we'll guess a bit larger. Same concept. We'll just guess somewhere between 0 and, if it's between 0 and 1, it has to be the max of 1 in the number. Because if you square it, it gets, if you take the square root, it actually gets bigger. That's of no consequence right now. And so we just keep on having that search space again, and you'll eventually get to the answer. And to check if your guess was too small or too big, you can say, like, your guess is, I don't know, you can always guess between 0 and the number, right? So let's say we wanted to find the square root of 2. We know the graph needs to look something like this, and we know our search space is somewhere between 0 and 2. That's where the square root of 2 must live. So initially, let's start in the middle. Let's guess 1. That's in the middle. That's 1. And that was too small, because if you square 1, it's smaller than 2. Okay, so now we need to put our search space needs to become this half. Okay, and you can keep on going until you approach the actual answer for the square root of 2 within any arbitrary bound that you want. All right, so it's essentially all this all over again. I don't really need to do much different, but I'll just change all these functions around. Double square root, double x, and let's output the square root of 2. 2.0, let's say. So again, guess between, I need the max function, guess between 0 and x initially. So double low equals 0, double high equals x, max of 1.0 and x. And while x minus, I don't know, 0.0001, absolute value of that, or, oh sorry, how do I want to do this? We'll figure this out in a second. When do we stop this loop? So let's first find our midpoint. Again, high plus low divided by 2, 2.0, I guess. So if we're really close, we're done. And that was what I was trying to put in the while loop, which was incorrect. So if mid times mid, so that's mid squared, minus x So we're trying to find the square root of x, and if we square it and it's close to x, then we essentially found that square root. Absolute value of that is smaller than some small bound, then we essentially found it. Return mid. Otherwise, if our guess was too big, let's say, if mid was bigger than x, mid squared, our guess was too big, and you know the drill. So our midpoint, our new high needs to be our midpoint. There's no concept of -1 anymore. Otherwise, we guessed was too low, and our new low, we need to guess higher, so let's make the low point the midpoint. I've been saying low like that. All right, and we want to keep on doing this as long as humanly possible, essentially until this happens. And, well, when do we want to stop this loop? Should it ever stop? Is it guaranteed to finish? It is essentially guaranteed to finish, isn't it? So we could do something like while low is less than high. That's kind of useless. It's essentially saying while true in the case of a positive number. But that'll, I think, help us if it's negative. But we should definitely be guarding against that. Ooh, and I think CMath has its own square root function, so let's call this my square root. Okay. And just to be pedantic, if x is less than 0, we got a negative number. There's no square root for that. Return, I don't know, -1, let's say. Negative number. Why did you do that? All right. So let's see if this works. And again, it's just having that search space. We started out guessing 1. That was in between 0 and 2. We squared that 1, found it was too small, so now we have to start looking here. And then we got 1.5 as our new midpoint, and we squared that. It was a little bit bigger than 2. It was somewhere over here. So now we knew that our new search space has to be in between here. So our new midpoint is 1.25. And that was a bit too small when you square that. It's less than 2. And eventually you're going to end up with that 1.4 whatever. Ah, yes. And so this is the case where we know it's always going to return, but C++ doesn't know. So if it gets so far as to never get here, return -1 as well, but we should never get there. And, oh man, we did it to a few decimal places, and that's exactly what we wanted. If we want to be even better, we'll put some more zeros. And now it's better than what it's going to print out. Yay. All right, that's the idea there. That's pretty cool, I think. I hope you like that. How are we doing on time? About a little over 30 minutes left. Or 25 minutes or so. All right, now on to that one question that we were talking about. Binary slash hex arithmetic. What's going on here? Well, it's kind of not exciting, is the idea. I'm going to teach you how to add in multiple bases at a time. It's really just like grade school, where remember, if you're adding 5 decimal plus 5 decimal, yeah, I gotta eventually, once you hit 9, you have to start carrying to get the 10, right? Now you have 10 decimal 10. That's the idea there. When you have binary, 1 base 2, 1 base 2, what's 1 plus 1 in binary? Well, it's 1, 0. You have to start carrying once you get to 2. Okay? That's the idea. So, with that in mind, how do we calculate 101 plus 001? Just like this. 1 plus 1, it's 1, 0 in binary. then we carried this. It's now 1 and 1. So this is, remember, this is 5 plus 1, and this is 4 plus 2, which is exactly correct. So it's 5 plus 1, it's 6, and so is this. This is also 6 in binary. Okay, let's do it a bit fancier now. 10, 10, 11, 01. Base 2 plus 10, 0, 11, 11. I encourage you to space this out more than I did. 1, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0, 1, 0. Well, let's see how badly I messed that up. So, 100, 111, 100. That was apparently 632 that I came up with. And the correct answer is supposed to be oh gosh, what did I do here? 10, 10, 11, 01, 10, 0, 0, 1, 1, 1, 1. Now, it's supposed to be 316, so let's see if I just did too many numbers here. This is... I had too many zeros at the end. There we go. Okay, I did it right. 2a plus b8, now in base 16. Okay. And this is essentially the same idea. What's a plus 8? Well, remember that a equals 10. So this is really 18 in decimal. So plus 8 equals 18 in decimal, which is 1, 0, in fact, in base 16. That's a 1, 0, that's base 1, 6. 1, 0, if I did that right. And now we have b plus 3, so b, c, d, e, if you count on your fingers. Should be E0, base 16. Let's see how badly I messed that one up this time. All right, 10 plus 8 is, that is in fact 18, which should have been, let's see here, 1, 16, 17, 18, so it's 1, 2, base 16. So this is really a 2. All right, let's see how good we did this time. So my answer was E2. The real answer was, yay, we did it right that time. Okay, now negative numbers. I've talked to you only about positive ones so far in this class. Like these 8 bytes, they make a positive number. These 8 bytes, they make a positive number. But that's not how it works in C++. When you have the int type, you can store negative values. So how in the world, in terms of bits, is that -1 being represented? And the idea is this. Negative numbers are represented using what's known as 2's complement. I'll put that in bold. And so we use an initial 1 at the start of a binary number. We use a 1 in the highest bit to represent a negative number. So in terms of integers, which are 32 bits long, there's 32 bits of any integer. So it's, I don't know, 1, 0, 1, 1, all the way down to 0, 1, 1. It's 32 bits for every integer. And the way you know if it's negative or positive is this first highest bit. If it's a 1, it's a negative. If it's a 0, it's positive. That's the idea. And so how do you know what is what? How do you know what's negative? If it starts with a 1, well, which negative number is this? All right? Let's pretend that we have 8-bit ints. So the 8th bit being 1 means negative. The idea is, well, here's some negative number. Let's figure out what -1 should be. Here is 5, 6, 7. The number 1. It's positive. If this has to be a negative number with a 1 in front of it, what in the world should we put here so that when we add all this stuff together, we get 0? How can we find what -1 should be in this representation? Well, let's figure it out. If we want a 0 right here, this should have been a 1. Then that means we carried. And if we want a 0 right here, that means we want a 1 here, which means we got 2 and we had to carry. And so on and so on. We'll figure out that, let me keep these on track, we need a bunch of 1s. So all 1s, in fact, it's not the largest negative number, it's just -1. Okay? And that's the idea. Because that final carry bit goes away, because we only have 8 bits with which to store things, that's how we can keep track of negative numbers and have them work just using normal binary addition. So, because that last bit is too big for the size of the 8-bit int, we're left with just 0, which is what we wanted. So that means all 1s is -1. All right, and now there's the trick to convert, or to negate, a 2's complement number. You first flip all the bits, and then add 1. That's the idea. So how did we know that this was -1? 6, 7, 8, if our ints are pretend 8 bits long only. Well, let's flip all the bits. This will convert it to a positive number. And then we'll add 1. And that's how we knew it was -1. Okay? And so -3, for example, it would be, let's start with +3. Let's flip all the bits. And then add 1. Oops. 1, 2, 3, 4, 5, 6. So that is -3. And if we add that to, for example, +3, just quickly, we should get 0 because of it. Or let's add it to like 2, so we get -1. -3 plus 2 should give us -1. That's exactly true, because we remember that all 1s was -1. And so this is beautiful and it's working. This is called 2's complement. So you flip the bits once, that gives you 1's complement, they say, and then you add 1, that gives you 2's complement. That's the fancy term for that. So yeah, that's pretty fun. And then finally, for these slides today, let's talk about, 2 last slides. Let's talk about some bitwise operations. So we've done like ands logically on booleans, ors logically on booleans, nots on booleans, but let's do them on individual bits, and this is quite useful sometimes. Let's pretend now we have like 4-bit numbers. You can do what's called bitwise operations. They work on individual bits of numbers. So let's first talk about the AND operation. It performs the AND operation on each bit of 2 numbers. So A and B, we say, performs bitwise AND on A and B. So this means treat each bit as true or false, 1 or 0, and perform the AND operation on each individual bit. So let's pretend I had 4-bit numbers, 1101, it doesn't really matter, 0101. If I were to AND these together, I'd do the AND on each of them. So true and true is true, false, true and true is true, true and false is false. So that's the AND operation. And this is quite useful for extracting bits. So if I just wanted whatever was at bit 2, or if I wanted whatever the value of the first bit was, I could just always take my number and AND by 1. Because if it was a 1, I'll get 1. If it was a 0, ANDing with 1 will give me a 0, and the rest is all zeroed out. So it's good for extracting individual bits. And so this is what the AND operation looks like for each individual bit, just like we were talking about. And then OR is the same. You just do OR instead of AND. And the only time you can ever get false is if they're both false. That's very similar. That's for setting bits, making sure that a certain bit was set. So like if I wanted to make sure that the second bit was set of this number, I can AND with 0010. Or sorry, I can OR with 0010. I just saw the AND and kept saying it. And so that'll do true, true or false, true, false or false, false, false or true, true, true or false, true. And so that made sure that this bit was set and just kept everything else the same. Okay. All right, not does the negation. It flips all the bits. And it's a twiddle. So not flips all the bits. So not of 1101 is just 0010. Simple as that. And then we have a special kind of OR. Whereas this normal OR that we're used to with like logical operations, it is true when both are true still. Exclusive OR means that only one of them can be true, and that'll make the final answer true. So exclusive OR means true, only if one is false and the other is true. So exclusively, only one is true. If they're both true, it's false, and of course, just like a normal OR, if they're both false, it's false. This kind of tests if bits are different. Exclusive OR, and it's called XOR sometimes. It's that little caret operation. And it's very similar to actual bit, to addition. And in fact, inside of your CPUs, for each individual bit to get what the answer should be, your computer is performing an XOR operation. Because if it's 1, 0, it's always a 1 in that case. If it's 0, 0, it's a 0. If it's 1, 0, it's a 1. And if it's 1, 1, it's a carry. So you got to have a 0 there. Isn't that cool? And then shift. Shift is super useful. This is where they stole these operators from for cout. This means bitwise shifting. Make something move up the bits, move down the bits. So this is shift up. Here's 101. I'm going to shift that up by 3 bits. This becomes 101 shifted up by 3 bits. So we're going to add some zeros. It moved that way. It added more zeros. You see that? And then similarly, 1011 shifted right by 2 bits. Well, this becomes 1, 0, because we got rid of these ones. They go away. Okay, so the number is kind of going that way and like it's falling off the edge here, kind of. That's the idea. So it's just moving bits around. And so if I want to get, if I want to use this AND operation, let's say, for example, check if the third bit of the number x is set to 1, what I can do is say x. Shift right by 2. So I'll get the third bit in the first bit's position. And by 1. And test if that's equal to 1. Isn't that cool? I'll put some extra parentheses because I don't quite remember the order there. But that's quite useful sometimes. All right. So that is Bitwise Operations in a nutshell. How are we doing on time here? Almost there. And then finally, for today, and in the next lecture, I'll just do a bunch of review, I think. Now we're going to talk about endianness. So this is how numbers are being stored inside of your computer. Let's figure out how that's working. So, like I said, a while back, let me just like draw a line or something for a new topic. Remember that your computer's memory can access individual bytes at a time. So at any address, you give your memory an address and you have it look it up, it'll get you back 1 byte of information. But sometimes, like in C++, we're storing ints at a time. We're storing 4 bytes. But many data types are more than 1 byte. How is that information arranged in memory is the question. And so your standard, there's 2 ways of possibly doing this. So like if I wanted to store these 4 bytes, let's say it's hexadecimal, 1B273AFF. If I wanted to store this in memory, so base 16, I could, let's say we stored it starting an address, I don't know, 12. I'll just use, that could be either hex or decimal. There's your address. Here's your value. So if I wanted to store these 4 bytes, here's the 2 ways I could do it. I could either just put them in order. So starting an address 12, we put the 1B, it's 1 byte. Then we put the 27, then we put the 3A, then we put the FF. Or, and this is like the logical way, or we could do it the weird way and do it like this, where the least significant bit, or least significant byte, we say comes first. And so we put the FF first. That's the first byte. Then we put 3A, the next byte, like that. Then we put 27, so it's kind of backwards. 1B, it's the weird way. And this weird way is called little endian. So like the little end, the smaller end of this comes first. And this normal sounding way is called big endian. All right, so those are the 2 ways you can store a large number with multiple bytes inside of your memory. Have it arranged just like that. And so that's exactly what this is talking about. And now I get to say that all of your computers are doing it the weird way. All Intel AMD processors actually use little endian, which is kind of funny, but that's just how they do it. And it doesn't really matter as long as when your CPU reads from memory, it just puts it all in the right spot. So they just chose little endian. There's probably a fancy reason. I am not a hardware person, so I don't know the real reason. But maybe it's because people want those smaller bytes first, and we want to have those closer in terms of like wires or something. I don't know. I'm just spitballing there. But that is little endian versus big endian, and you have to live your life with a computer with a little endian style of storing things. Isn't that fun? So that's endianness. And then finally, Just one last comic, I think. This is the end of these slides. And I think, yeah, so this is the last set of slides that I have. And so in the next lecture, in the final lecture, I will just give a review of all of the stuff that is here on our final page. I'll just go through all these topics as much as I can. I've made this little file. I'll keep it posted in the same folder. I already put it up here. It's called review.cpp. And so I'll just start here next time and just go through it all. I might take extra time, but who really cares? It's a review. So that'll be the final lecture. And yeah, that's all I have for you until then. So I will see you in our last lecture, lecture 17.